My name is Riccardo Lippolis. I'm a software developer working for JDriven, a company in Nieuwegein, Netherlands. But I'm situated in Rotterdam, and for the people here from the Netherlands know how hard it must be for me to be here in Amsterdam then. But yeah, I'm doing this for you guys. So I've been a Java developer for, more than 10 years, I think, 15 years by now, of which the last few years I've been doing Kotlin. Started working with Kotlin on my current project, which is a route scanner. It's basically a routing engine for multimodal container routes all over the world. And with containers, I mean shipping containers, not the Docker variant. So you can imagine that building a routing engine has some challenges that needs to perform well. So concurrency is something that we can really use in our project. And yeah, so we decided, why not use coroutines, seeing as we're already doing Kotlin. And we started using coroutines, but not in the right way. So along the way, we learned what we did wrong and what we should have done better. So I decided, okay, I'm probably not the only one that's making these mistakes, so maybe I can share my knowledge about coroutines and help you by not making the same mistakes I did. So this is not a very advanced talk into a deep dive into coroutines. This is more like a way of trying to make you understand the concepts around coroutines that I hope that in the end, when you've seen this presentation, you're like, okay, it clicked. In the Dutch, in Netherlands, we say kwartje is gevallen. And that you know how to apply coroutines and you can start experimenting with them yourselves and have fun with them. So what's a coroutine? I've given a definition. So they're basically program components that generalize subroutines for non-preemptive multitasking by allowing execution to be suspended and resumed. So when I read this, I'm like, okay, why would I want non-preemptive multitasking? What is it? And suspending and resuming functions, probably most of you have a sort of Java background and you're like, we call a function and it returns something. How do we suspend and resume them? I mean, that's a weird thing, right? So I'm gonna dive into those topics. Starting with non-preemptive multitasking. Again, the definition, don't worry, it's not going to be all definitions all the time. I've highlighted the important parts. It's about multitasking and in the same way, preventing context switches as much as possible. In the definition it says never, but never say never. You try to switch context as less as possible to be able to do efficient multitasking within the same context. And the way that it works is that the different tasks that are running in parallel, they voluntarily yield control to other tasks while they are busy. So basically, it's multitasking that works because the tasks have manners, let's say. So imagine a single lane road. On the picture, there could be two cars coming from different directions. And of course, if one car uses the passing lane, then the other can pass. So if the car drivers have manners, then you can use have multiple cars simultaneously on that single lane road. But of course, if some drivers are egotistical, if nobody uses the passing lanes, then of course you have a blockage, and then the whole thing stops. So the principle is that the tasks do yield control occasionally to make this work. So to give a more concrete example, I'm half Italian, so of course when I try to relate something to the real world, I think of food. So I've said, okay, what's a multitasking thing that you can do by yourself? So, that's cooking. So I've decided to implement this cook pasta function, which is basically a very simple recipe for pasta. I know Italians can be pretty, religious about their dishes, so maybe I'm offending some regions in Italy now, but I mean, it's just a basic recipe. But I think all Italians can agree that we don't use ketchup in the pasta. Not even Kotlin ketchup, which is actual Kotlin ketchup brand in Poland. So please, no ketchup. I think then we can all live together in harmony. So, yeah, it's the function cook pasta is split into several steps. They're pretty self-explanatory. You know, you boil some water, you cut some vegetables, you put it all together, you prepare the pasta, and then in the end you serve the dish. So you can see that, they're pretty straightforward steps. The way I've implemented the functions is by just using thread.sleep, so I cheated a bit. But just to give an indication that every step takes some time to complete. If you look at this dish, you can the recipe, you can already see that some steps belong together more than other. For example, you have the cooking of the pasta, which consists of boiling the water, adding the salt, and cooking the pasta, and you have the preparing of the sauce, which involves cutting some vegetables, and in the end, when all these tasks are complete, you can serve the dish. So you already see some dependencies, but here it's just a sequential list of tasks. So, well, we execute this, and basically it runs as you would expect. All the single steps, they are executed sequentially, which is not the most efficient way, of course. And in the end, after 35 seconds, we have a pasta dish. Well, of course, in reality, I'm not that fast with cooking, but just to give an indication, it's a random time, 35 seconds. So, how would it be when we're using coroutines? This is a way of doing it with coroutines. I'm not saying like, okay, copy this into production. It's just to give an indication what it would be like if we would do it in a coroutine way. So what changed? You see in the function definition a few new terms, suspend function, and you see something with coroutine scope. I will explain those later. And the implementation of the different steps also have two changes. There are also a suspend function, and instead of a thread.sleep, I use delay, which is basically the same, only, spoiler alert, it's non-blocking. So also what I changed is the grouping of the different steps. So as I mentioned earlier, we basically have two components. We have the pasta and we have the sauce, and we have to prepare those both, and in the end put it together. So I've grouped those into an async function block. So preparing the pasta, making the sauce, and then when I've defined those tasks, I wait until both are ready, and then I serve the dish. So there's a more dependency style of, a grouping of the different dependencies, so it's more clear what belongs together. So I'm running this. Hey, 20 seconds. Wow, a lot faster. And what's also interesting to see is that the different tasks are intertwined. So we have the preparing of the pasta, the preparing of the sauce, and in the end we say, okay, well, we're serving the dish. Nice, right? But what blew my mind when I started working with coroutines is it's all running on the main thread. I mean, it's single-threaded, but still we're doing multitasking on one thread. Like, what's going on? Is this magic? No, of course not, because we're in IT. Everything appears to be magic at first, but then we read the documentation and then we know that it's not magic. So it's just suspending functions. So, like I mentioned before, a suspending function, you can suspend and resume it. And that can mean that if a function has to wait for some long-running operation, probably you're already thinking of stuff like I/O disk, database access, and whatever. They can suspend, and they can do that without blocking the thread that they're suspending on. So it's not a sleeping of the thread, but basically a suspending of the task. So a suspending function can be created in Kotlin by using the suspend keyword. And basically this keyword, suspend, is the only language feature of the Kotlin language needed to implement coroutines. All the other stuff, that's all under the water in the Kotlin coroutines library. But in terms of language features, you only need the suspend function. And, well, when does the function suspend? At the point where it's calling another suspending function. So we saw the delay earlier, we saw yield. No, we didn't see yield, but basically a delay can be seen as a yield with a minimum time period. And I'm saying minimum because obviously when, same with thread.sleep, if your thread is blocked, or like if their resources are not available the moment the thread needs to wake up again, of course you can continue. But normally, in normal circumstances, you sleep for the given period. But also when you're calling another suspending function that you've defined yourself, then also that's a suspension point. So what happens basically under the hood, I can show the JVM bytecode, but I probably see a lot of people running away then if that happens now. So basically, I think in the afternoon there's another session that does a deep dive into the JVM implementation specifics for Kotlin. If you're interested in that, then you can visit that session or just afterwards come to me and I can explain it. But basically what happens is that by using the suspend keyword on your function, the JVM bytecode for your function looks totally different, and it's basically manipulated into sort of a state machine where every part of the function up until the next delay, the next suspension function is one of the states of that function. And then that means that basically the coroutines library can call your function, but start at a different point within that function based on the previous state. So it's a pretty neat feature. I think or hope when Project Loom arrives in Java with the virtual threads that maybe there's going to be a more efficient way of implementing this on the JVM. But I mean, it's not that it's very resource intensive, but of course there is some overhead in calling suspending functions. So yeah, well, we explained what happened. So the moment the boil water function is executed and the delay is called, at that point, basically under the hood, the function returns, giving the coroutines library the possibility to call the next method, the cut vegetables method. So that's, I mean, I hope that the magic of the coroutines is a bit unraveled at this point. I've talked about the suspend function, so the other part was the coroutine scope. So what's a coroutine scope? To explain that, I need to explain the concept of structured concurrency. So structured concurrency has a pretty big definition. I'm not going to bore you with another definition, so I'm just going to give you the short version. What that means is that you can, well, as the term says, structure your concurrency using imperative program flow. So what's imperative program flow? Well, I mean, you've all probably been using it, like for loops, if statements, when in Kotlin, just one function calling another function and that function returning something. So really the traditional way of imperative programming. What guarantees does that provide you? Well, that means when in imperative programming function A calls function B, you know that function A won't finish until function B is ready. So A calls B, B does its thing, returns to A, and then A can continue. And because you're using the same principles in structured concurrency, even though you are running things concurrently, you can still reason about the execution order of your concurrent code. Because you get the guarantee that if there are child operations that are run asynchronously, they all finish before their parents finish. Also, when one of the child jobs or task operation, whatever you want to call it, child functions, throws an exception, automatically the framework, the library of Kotlin Coroutines makes sure that all the other child jobs that are still running are canceled. So it automatically gives you some cleanup process, which helps a lot in writing clean code. Because, well, for the people that have already some experience with building this themselves, like maybe using a thread pool for child tasks and then spinning them all up, and then, well, something goes wrong, and they have to clean up everything and close the thread pool, etc. There's a lot of boilerplate going on in there. And of course, I mean, you can achieve similar things, but it's just a lot more code. So this provides you a way of writing concurrent code in a very clean way. So what would that look like if we applied it to the pasta dish? What I've done here is basically wrote two separate functions for the different parts that are that belong together. So we have the pasta and the sauce. Two separate functions, very straightforward. There's a prepare dish function where we say, okay, well, if we want to prepare the dish, we need to launch two separate tasks. We need to prepare the pasta and make the sauce. And here I'm using the coroutine-scope function that's provided to you by the Kotlin library, which enables me to use the launch function and also the async function we saw earlier. Basically, you could say that a suspending function is a coroutine scope of its own, but if you want to launch more more asynchronous tasks, then you can use the coroutine scope builder function, which helps you, which provides you with the functions to launch stuff. So what's the difference between async and launch? It's basically launch doesn't have a return value, or, doesn't return any data, and async provides you with sort of like a, you could call it a future or a promise, but in Kotlin language it's called a deferred, but it's basically the same, the promise for some data somewhere in the future. So in this case, I mean, technically preparing pasta returns pasta, but in this case, because it was a function returning unit, I can use launch. And the serve dish function is called after the prepare dish, and because we're using structured concurrency, even though the prepare pasta and make sauce functions are launched asynchronously, we have the guarantee that serve dish will only be called after the whole prepare dish function is ready, meaning that both the pasta and the sauce are ready. So it's very easy to read this, very clear to know what's going on. And yeah, so that's concurrency in a readable way, and that's amazing. So, well, I mentioned earlier about error propagation. So error in one child operation will cancel the others. So let's say in the boil pasta, an exception is thrown. Of course, should never happen, but we all know in production those things do happen. And, well, the boiling of the pasta goes wrong. So what happens? The exception is thrown, and we get a typical stack trace as we are familiar with in our normal day-to-day work if you're doing JVM Java development. The exception is thrown, and the whole execution stops. So even though we started cutting the vegetables, that coroutine is also cancelled by the framework, and yeah, everything is stopped. The whole pasta preparation stopped. So that's nice, and then you get a nice stack trace, and you see in the stack trace already an invoke suspend line. So that's like the JVM bytecode manipulation that's going on underwater, but you also get a nice line number at the boil pasta function where it actually happens. So it's also easier to debug your errors, to know where it went wrong. Well, so far we've all done everything single-threaded. So can we use multiple threads? Well, of course, if you're not using Kotlin JS, because, well, JavaScript only runs single-threaded. And of course, you can still have the benefits of using doing multiple tasks on one thread, similar to the async await style programming in JavaScript. But of course, if we have multiple threads, we want to use multiple threads, and we can. So to explain how to do that, I need to take one little step back and explain the concept of a coroutine context. So every coroutine is executed within a certain context. And of course, context is a very broad term. I mean, it's a really vague concept, right? But context just means, well, along with running the coroutine, there's a map of key value pairs that have some information about that coroutine. And you can add your own key value pairs to that map to provide some context that applies to your application, but there are also a few default context elements. And the elements basically the key in that map. So one of the elements that's always there is the coroutine dispatcher. And dispatcher basically determines on which thread your code is going to run, your coroutine. So we can override that in the child coroutines called from a certain parent context. But if you override the context, it's only overridden from that point on. So if coroutine A calls coroutine B, and in B the context is modified, it's only modified for B and everything else that is called by B. But A still retains its original context. Again, very easy to reason about when reading the code. So let's do it multi-threaded. What's changed? Well, I'm using the withContext function and providing dispatchers.default. So I can imagine a bit of confusion here. That confused me in the beginning as well. So one of the things was, well, why am I specifying a default? Shouldn't that be the default? No. So the term dispatchers.default must be read as it being a default dispatcher that's provided to you by the coroutines library, but it's not the default one being used. The one that's being used is determined based on where you're coming from, and I'll explain that later, but just remember for now that dispatcher.default is not always used by default. And the other thing that confused me was that we're calling a withContext function, but we're passing in the dispatcher. So is a dispatcher a context then, or like what's going on there? No. The way you need to read this is that we are enriching the context of the coroutine with a dispatcher. And it's just a convenient way of specifying this instead of needing to expand the context yourself with some new element. You can just specify a context element and it's added to your context. So we're running this, and woohoo, we have multi-threaded. As you can see, the boiling of the water and preparing of the pasta is done on worker thread 2, just randomly chosen. And the cutting of the vegetables and the preparing of the sauce is done mostly on 3. Nicely multi-threaded pasta cooking. And in the end, we are serving the pasta on the main thread again, because as I specified before, child coroutines can override their own context, but the parent context remains the same. So the parent function was calling the prepare pasta function, and that function specified another dispatcher, but the main function, the original calling function, still had its own context, so still operating on the main thread. But what's also interesting here is to see that both the pasta is ready and the sauce is ready line are on worker thread 2. But I mean, I thought like one was on worker thread 3 and the other on 2. Well, no. What happens there is that coroutines are not confined to a single thread. So every suspension point where your function is suspended, after resuming, it may resume on another thread. So that's something you need to keep in mind if you're doing stuff with, thread locals, transactions, security, which are often things that use some sort of thread local state. That's not going to work out of the box on Kotlin Coroutines. Of course, there are ways to make it work, but just be aware that if you're doing something with thread locals, then by default, you need to bridge that to the Kotlin Coroutines way. And that's also the benefit in some way, because, because after the pasta is ready, logging statement worker 2 was done, he could just immediately continue with another task that was waiting, and that was the sauce is ready function. So there was no need to wake up worker thread 3, but we could just reuse worker thread 2. So that's also a more efficient way of using your worker threads. So what kind of dispatcher types are there? Well, I've specified dispatchers.default. It's basically, you could call it similar to the fork join pool in Java. It's just a common pool that's where the size is determined by the number of CPU cores, and it's always available for you, can be used. There's a dispatchers.io type that's for offloading I/O tasks, and of course we try to do things non-blocking when we can, but sometimes, well, you just have to block. And for that, there's a separate dispatcher. It's called dispatcher.io. You can offload it to that dispatcher. It's like a growing pool of waiting threads, basically. But it's easy to just offload it to that pool so that your computation code can still continue on the other dispatcher. So if you're doing UI development, for example, with Android or JavaFX or Swing, there's a dispatchers.main. When you're doing UI development, you know that if you want to update the UI, you always need to do that on the main thread or the main event loop of the UI system you're using. Well, there's a convenience dispatcher for you, so that when you need to update the UI, you can just say with context dispatchers.main and then update your UI. And the good thing is, because you're obviously doing everything non-blocking, even when you're waiting for data from somewhere over the network or reading from disk, you can just call the suspending function. And even though you're running that on the main dispatcher, the moment it wants to block or, well, suspend, it just suspends the function and other functions can resume. So it prevents your UI from blocking. So that's great. As long as you obviously don't do any actual blocking on that within the main main dispatcher context. You can also just create your own Java executor, the typical stuff that's present in JVM by default, and just convert it to a coroutine dispatcher with a function that's provided to you. This way you can, for example, say, well, I want to have a thread pool, an executor pool of at most 4 threads, which simultaneously do things. So it's a pretty nice way to limit the parallelism of your code. So far, we know that, well, suspending functions can call other suspending functions, and, well, all coroutines are executed within the coroutine context. So how do we get there? How do we start? Well, there are a number of ways. I'll start with the worst one. There's a thing called Globalscope, which is a global application-scoped coroutine scope. So that I say it's suitable for one-off tasks, one-off async tasks, and, well, suitable is between quotes because there are some downsides to using it. This global scope does use the dispatchers.default by default. So if you use the global scope to launch some asynchronous task, it is done on another thread. So if we're using this, what would that look like? Well, imagine we want to save some entity to a repository and at the same time also publish an updated event. You can imagine that, well, you don't want to wait for the event to actually be sent, so that's something you can just fire and forget, basically. Of course, here I'm forgetting the whole transactionality thing, so if an exception occurs during save, then yada, 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 but that's not important for now, just to give an example of what it would look like. So there's a globalscope.launch function, which can be called from non-coroutine code, which launches that piece of code on the default dispatcher, so on another thread, basically, and it returns immediately. Of course, what goes wrong is, well, if there's an exception within that launch block, it's pretty hard to pinpoint where exactly it came from, because, well, basically you're losing your context because it launches the task somewhere else, and basically it's more like a fire and forget. And it's hard to manage exceptions and errors, etc. So and the other downside is, well, if you're using globalscope.async, which has a return value, like I said, a deferred, which is like a future or promise. Well, then you have that deferred object, but yeah, how do you get the data out of it? You can't call await, because await is suspending function. So you're sitting there with your deferred, and yeah, well, what are you going to do? Like a while loop, and then, I mean, yeah, there's no clean way of getting the data again. Instead of using a global scope, what you can do is you can create your own coroutine scope if you do want to have a separate scope, which is linked to some life cycle. So, for example, the life cycle of a Spring Bean. If you're using Spring, you can automatically close that coroutine scope when your Spring Bean gets destroyed, which means that all tasks that are launched on that coroutine scope are all cancelled. So, and with Globalscope, well, it's fire and forget. So all the things you've launched, they are still running somewhere in the background, and you need to manually stop that. So when you're using your own coroutine scope, for example in Spring, but also if you're using Android development, like link it to an Android activity, so that when the activity finishes, then it closes the coroutine scope, then you know that there won't be any dangling jobs running somewhere. There's another way. If you're want to run coroutines more localized, so when I'm talking about coroutine scope, it's obviously linked to some application lifecycle or some lifecycle, but if the lifecycle is basically your function, what do? You can call run blocking. It sounds a bit scary, run blocking, because, hey, well, we've been talking about being non-blocking all the time and not blocking anything, and now all of a sudden we are blocking, but in this case it's something you want, because basically what you want is you're in a normal context and you're calling some code that uses coroutines, and that whole block you want to have finished when your function returns. So basically you are blocking your own function in calling that piece of code. So it's a valid way of naming it, but it's something that you want. By default, that runs single-threaded on the thread that calls run blocking. But you can also specify your own dispatcher to do some multi-threading. So if we're going to use that in the same example, what would that look like? We have the save function, which calls run blocking, and it passes the I/O dispatcher. Well, because we're doing I/O, right? We're saving an entity to some repository, and we're sending an event. So that typically involves I/O. What happens here is that when some function calls the save function, run blocking here basically means, well, the whole thing is blocking until all the stuff within the function is actually executed. And that's, well, basically what we want. We want to asynchronously save the entity, and we want to send an updated event. Of course, again, here, when one of those two goes wrong, then, yeah, it's not very nice, but just to give an idea again. And when we want some data in return, but in the meantime do something else, we can use run blocking again, where we call some HTTP client to get some data, and we're running that asynchronously on the I/O dispatcher. And while that is running, we do some other stuff, and then in the end, we can call await, which is a suspending function. And the moment the HTTP call was done, we get our data and we can return this as a whole. And what we're returning here is some data, and that is because the run blocking basically returns the last statement within your block. So in this case, remote data.await returns some my data, and that's returned from this function. No. So yeah, hopefully you can find a way of doing everything front to back in a non-blocking way. So of course there are also libraries and frameworks to help you with that. So for example, if you're using reactive Spring, like Spring Webflux or Spring R2DBC, you can be fully reactive and using Kotlin Coroutines in between. So that means that your REST controllers can be suspending functions. Instead of being a function that returns a mono or a flux, you can just make your function suspending. And the same when you save an entity to the database or when you retrieve an entity from the database. Instead of retrieving a mono, you can just create a suspending function which returns the actual object, but because it's a suspending function, it only returns object when the data is available, and all that in a non-blocking way. So you don't need any global scope or run blocking. It's all coroutine scope front to back. Of course, if you're not into Spring, but more like Quarkus, Micronaut. They have similar approaches. And basically that is because, well, there's good interoperability between Kotlin Coroutines and some typical reactive streams libraries like RxJava, reactive streams, Project Reactor. Of course, Spring uses Project Reactor, so that explains why. If you're using, for example, Ktor or some other non-blocking HTTP server client, there are also ways of using it. So it's there's broad support for coroutines. Seeing as we're almost out of time, I'll go through this a bit faster. They're very lightweight. So here what I've done, I've written 2 pieces of code. The first one launches 100,000 threads and just calls thread.sleep. And the second one does the same, but with 100,000 coroutines. And you already see on the right side that, well, in terms of memory, and yeah, the CPU is not included here, but it's the same. There's a big difference in the number of resources needed to run this. And of course, if you run 100,000 coroutines, which actually does something important, then there's more memory involved. But just to see that the overhead of running coroutines is relatively small. As I've mentioned it before, that you can cancel a coroutine. So what does that mean? I mean, back in the day, we had thread.stop that was removed from the Java API at some point for valid reasons. So why are coroutines cancelable? Well, basically because, well, we have suspension points. So when a coroutine suspends at some point, well, we don't have to resume it. We can just stop there. So when you call cancel on a coroutine, that means that at the next suspension point, it's finished. It doesn't resume anymore. And of course, you have to make sure to clean up resources. There are ways to do that, but you know, it's a very clean way of canceling running tasks. I'll skip these for now. As if you're using reactive stuff, you know about cold observables, hot observables. Well, there are some ways of doing that in a very clean way. I have an example project which is built with reactive Spring using Webflux on the front side and R2DBC on the back side with coroutines gluing that all together. It's a very, functionally stupid service which does some calculations and also returns whether or not the number is even or odd. But, I mean, it's just to give an example of how you would combine, for example, HTTP calls with database access all in a non-blocking way. So thank you for attending and thank you for listening. I hope you learned a lot about coroutines. Maybe we have time for questions. Otherwise, I would say enjoy your lunch.
Any questions for Riccardo still? I see 2. Go here first.
Hi, thanks for the introduction to coroutine. So I've actually seen several of these introductions to coroutines, and always like error and resource management is absent. Like you never talk about it, which leads me to my actual question, which is how hard is actually dealing with like errors or resource handling, this kind of more complicated stuff. Does it still look as nice as what you've shown on the slides, or do you really have to make a mess to handle everything correctly?
Yeah, so a valid question. Of course, typically in presentations, you don't use real-life full production software. It's obvious that, it depends on your coding style. If you are splitting everything up nice in small functions, then you can achieve very nice stuff. Compared to doing this without doing stuff like that without coroutines, you need a lot more boilerplate. And coroutines gives you the option of doing the same with a lot less boilerplate code. But still, if your resource cleanup code involves a big mess of code, then yeah, the whole thing is still going to be messy. But well, the boilerplate is a lot smaller, so it can still look nice depending on the rest of your code. That's the short question, short answer. Does that answer your question?
Sort of, I guess.
Oh yeah, well maybe I can give an example. So I hope this is readable, but basically what you can see here is, well, we're using Globalscope, ignore that for now. If you launch something and you want to have some cleanup, you can just use a try and finally, like you're used to in Java. And within the finally, you have to say, okay, this part is non-cancelable because, well, if you're doing some cleanup and, well, during the cleanup something suspending is called and you were already canceling the coroutine, you still want to execute that. So there's a way of saying, okay, this block needs to be run and not be canceled. So yeah, what's the overhead here? Well, you have to try and finally, and you have some a with context block that's non-cancelable. All the other stuff that's just, well, yeah, determines on your use case. So it's not a lot of boilerplate to be able to support resource cleanup, right? So it's still pretty clean.
Hi, is run catching is a preferred way to deal with exceptions?
Oh, you're talking about run catching or?
Yeah, run catching is
okay.
like run blocking, run catching.
Yeah, well, run catching is, of course, it's not a coroutine library function, but it's more like a Kotlin standard library function. But yeah, I like it because yeah, it gives you a way of yeah, it's basically like a Kotlin way of using a try finally or try catch block, where you can yeah, use the more functional style of implementing a try catch block. But yeah, I like it, but yeah.
I mean, it's a good
yeah, it's a good way
thing to use.
I mean, the implementation of run catching is basically a try catch block, but yeah, it gives you some nice like a get or else or a get, you know, so it's yeah, just use it.
Cool. Give it up for Riccardo again. Oh, sorry.